This video is going to provide an overview of how enzymes function, how we discuss enzymes, and some tools scientists use to be able to understand and anticipate enzyme functions. Before talking about enzymes as a new thing, let's first review how enzymes come about in the first place. We know all enzymes are made of proteins, which means that they're made up of amino acids. All of those amino acids have different R groups, and those R groups themselves create the binding site where the reaction is occurring. The enzymes have to bind to a substrate, and the substrate specifically binding with some part of the R group of an amino acid is literally what determines the binding of the amino acid of the substrate to the enzyme. So let's give a couple hypotheses. If we've got one amino acid that's in the binding site and it changes from glutamic acid to aspartic acid, would this make the enzyme dysfunctional? No, this would not make the enzyme dysfunctional, because we're going from one amino acid that is acidic to another acidic amino acid. And as acid to acid, they're still going to be able to bind with whatever the substrate is, because those are still both acids. Whereas one amino acid changes from glutamic acid to arginine. So now we're changing from an acidic amino acid to a basic amino acid. And will this make the enzyme dysfunctional? More than likely, yes, at least a little bit more dysfunctional, because that one specific amino acid is no longer able to bind in the substrate. And so that substrate isn't going to be binding as effectively or efficiently into that enzyme. And so you're going to end up needing more energy for the reaction to occur because it's not stabilizing the transition molecule. We'll talk more about enzymes and transition molecules in upcoming slides. So what is an enzyme? An enzyme is always a protein. All proteins are not enzymes, but all enzymes are proteins, and they are also used to catalyze a chemical reaction. A catalyst is something that speeds up a reaction specifically by lowering the activation energy. That activation energy is the energy needed for the formation of the transition molecule. So a catalyst is some type of molecule that is going to lower the energy of the transition state. That could be because it's changing the actual structure of the transition state. That could be because it's removing some of the tension in the bonds by allowing it to bind with other things in the active site of the enzyme. But in some way, catalysts are always going to lower the energy of the transition state molecule. All enzymes are catalysts, but not all catalysts are enzymes. So you can have other things that speed up a reaction by reducing the energy of the transition state that are not enzymes, but are, by definition, a catalyst. So if you have an enzyme, that is going to specifically stabilize those bonds in the transition state. If you have a reaction going from the reactants to the products, there's going to be a hump where there's going to be an increase in energy before that final energy change occurs. Whether that energy goes from negative to positive, there's still going to be a hump more than whatever is the beginning or the end state, that is the transition state. That's also considered the activation energy. So if we think about an enzyme like a 3-year-old who's throwing a tantrum, so let's say we have a reaction occurring, and this reaction, if it's occurring without any help, we can think of that reaction like a 3-year-old throwing a tantrum, where there's just going to be arms flailing, a whole lot of energy, a whole lot of excess energy being spent. And that transition state, or that middle part where the tantrum is actually occurring, is a lot of energy. There's a lot of energy there. In order to reduce the amount of energy there, you can go in and intervene. So by you intervening, you're able to calm down the baby. You're able to make it a little bit more of a chill situation. That is similar to what an enzyme is doing. They're reducing the energy of the transition state, or making that baby calm down when they're throwing a tantrum. So there's a couple different ways in which you can go and intervene with this child. You can do one, just whoop the kid a couple times. You have to be very aware of how your energy is being spent when you are whooping a child. It's going to have direct contact You're not going to be able to avoid it by chasing and running after the child. At a certain point, it's going to be direct contact of actually whooping, but you want to be aware of the line between abuse and correction. And you have to control your energy. You don't want to be using excess amounts of your own energy on the child because you may end up hurting the child, but you also want to be effective enough to get your point across. That's one option of doing it. You can also start with a conversation, but know that you have a switch necessary if it's necessary. You got it in your backhand. So this is more of the like people who are attempting to do soft parenting where it's like, okay, let's start by talking about your actions. And then the child is still screaming at you. And so you're still trying to talk. We're going to try and talk. We're going to try some options. But at the end, like last resort, we're going back to just whipping it. Like we're going straight to what it is. I'm not going to try any other strategies. You're not receiving any other strategies. So we're going to do what we're going to do. You have to be a lot more aware of when your energy is getting too much or too little, because you don't just have, okay, this is what I'm going to do. This is my one strategy. You have to be a little bit more flexible in what you're doing. The same hypothesis occurs for how enzymes function. There's two options. You can either have the active site model where, okay, you've got an enzyme, you've got the substrate, and it just fits one way. There's only one way for it to fit. If it doesn't go in that way, it won't fit. And it requires a very specific amount of energy. You can also have the induced fit model where an enzyme is going to shift itself around depending on how much energy it's going to need to absorb. So an enzyme in an active site model, there's one enzyme, one substrate, lock and key is basically how it is, the concept of how it fits. There's only one way to get it done. Any switching around is still not going to happen. Whereas an induced fit is kind of like mold, like a clay trying to mold into something. So that clay can be molded into a pot, it can be molded into a bunny, it can be molded into a lot of different things. But depending on what it's in is going to determine how it's acting. That's the induced fit, where you're going to have one enzyme, multiple different substrates, and that enzyme is going to shift itself around to fit in that substrate, depending on what that substrate actually looks like. Either way, the amount of energy required for it to reach the transition state is the activation energy. So whether that's going to be the induced fit or the active site, both of those have a certain amount of energy that's required, and that is the activation energy to make the reaction occur in the first place. So if we wanted to put this on a graph, you can put the x-axis being the substrate concentration, or the amount of substrate that's around in this reaction occurring in the first place. And that is going to be on the x-axis because it is independent. That can be independently changed, and you don't have anything happening based on that. The thing that you are going to be measuring it against is how well the enzyme is functioning. And you can measure that based on the quickness of the reaction. We talked about enzymes being catalysts speed up the rate of a reaction. So an enzyme should have a faster reaction or a faster velocity if there is more substrate around, in theory. That is how this graph comes across, where you have the substrate concentration on the x-axis, and then on the y-axis, you've got the reaction velocity. That is reflecting, based on the amount of substrate concentration, this is how quickly the reaction is occurring. You can think of this like, okay, well, there's only one enzyme, but we've got a whole lot of substrate around. Well, this enzyme is going to be working at one specific consistent rate. It can only do one substrate at a time. But now, let's say we've got a whole lot of enzyme around, but we don't have very much substrate. That enzyme could function more if there was more substrate around. So if we increase the concentration of the substrate, that enzyme is going to be able to function more. But the maximum velocity, that point where, okay, this is one enzyme, it doesn't matter if there's more substrate, the enzyme can only do one thing at a time. That's the maximum velocity, or the Vmax. So then from the Vmax, you can also figure out the substrate concentration where you're at half of the Vmax. So, okay, if this is 100% efficacy, where are we at 50% efficacy? If the Vmax has a certain substrate concentration, then half of the Vmax should also have a specific substrate concentration, right? And so the point where you're at half of the Vmax, that substrate concentration is called the Km. And this is a constant. Anytime you see K in chemistry or physics or any science, it's going to be a constant reflecting something. And in this case, this is the Michaelis constant, Km. We'll talk about who Michaelis is. We honestly aren't going to talk about who Michaelis is because it really doesn't matter who Michaelis is. That was just one person who came up with one way to talk about enzyme functions. So we have Km for the constant reflecting the M&M kinetics. This is incredibly important because you can anticipate if this Km changes, it may or may not mean the Vmax is changing. The Km is a substrate concentration, so it's independent. But that Vmax can be changed depending on where your depending on when Km falls. So it could take a lot longer to reach Vmax if your Km is higher than if your Km is lower. And this also can help you tell how effectively or efficiently an enzyme is working. If you have a really, really low Km, or it takes a really, really small concentration for it to reach half of the Vmax, then you can say, oh, this enzyme fits really well with the substrate. When these things fit, the reaction occurs really, really quickly. As opposed to if it takes longer, you can say, oh, this substrate is either there's something else fighting to bind with this enzyme, or this substrate doesn't bind very effectively with this enzyme. And so it's taking a really long time for this reaction to occur. That also can change how high this Vmax is. The Vmax can change if there are things that are preventing the substrate from binding to the enzyme directly. So as stated, Km is substrate concentration where half of the active sites are bound by a substrate. And the Vmax is the maximum velocity of the enzyme, how quickly the reaction can occur. At this rate, the reaction won't occur any faster, even if you give me more substrate. All of the enzymes are completely filled. And when there's no more substrate that you can add, when every single enzyme has a substrate bound to it, you can think of this as being saturated. In the same way that like lipids are saturated and unsaturated depending on how many hydrogens the carbon's attached to. So if you have like all of the carbons attached to as many hydrogens as possible, you can't add any more hydrogens. That's a saturated lipid. Same here. When the enzyme is fully saturated, you can't add any more substrate and change how much this enzyme is going to be functioning. All of the active sites already have a substrate bound there. So then from that plot, you can also do some math wizardry and get to another plot, which is an LB plot. They call this a double reciprocal plot. And the reason they call it double reciprocal is because there's two reciprocal meaning like inverse or like flip the whole thing, and double meaning we're doing it twice. So on the previous graph, you had the x-axis being the substrate concentration and the y-axis being the velocity or the Vmax or the reaction velocity, where it goes up to the Vmax. On this thing, the theory is that lines are easier to see than curves and are easier to interpret than curves when it comes to doing math. So we're just going to like magic math to get ourselves to have a line and then interpret this line. That's one of the maybe goals of why they have this line situation created. But the things that are really important when it comes to being like tested or asked about this LB plot are where's the Vmax, where's the Km, what is this changing if it comes to some type of inhibition. We're going to cover inhibition in future videos, but as it relates to like what is the Km, what is the Vmax, let's just talk about the LB plot in the first place. Double reciprocal. Let's first talk about reciprocal on the y-axis because it'll be a little bit easier. So reciprocal, like I said, goes flipped upside down. So instead of having the V or the reaction velocity, you've got 1 over the reaction velocity. And so if you think about fractions, if you've got 1 over something, anytime the bottom number gets bigger, the fraction overall gets smaller. So let's say if we have a V of 5 versus a V1 is 5, and then we'll call V2 10. So then 1 over V1 would equal 1 over 5. And then 1 over V2 would equal 1 over 10. And although 10 is greater than 5, 1/5 is greater than 1/10. So you can see, although on the other thing, if you see the V going up, you can anticipate the velocity is getting higher. Here, if you see this 1 over V0 or 1 over the V, if you see this going down, you can anticipate it's getting bigger because the fraction would be getting smaller. So this 10, although this velocity gets bigger, after you do the reciprocal situation, this fraction gets smaller. So that's going to correlate. If you see Vmax going down, that's going to mean that the velocity is actually increasing. I'm sorry, if you see 1 over V0 going down, that means the Vmax is actually increasing. It's backwards. And for the x-axis, because it's 1 over the substrate concentration, we've got the same situation happening here, where if the denominator or the bottom number gets bigger, the overall fraction is going to get smaller. So if you increase the number of substrates, you're going to decrease the overall fraction that you see. But that is going to go related because the substrate concentration was reflective of the Km thing. And here, if you just look at this graph on this side, so where it's in the positive X and positive Y, this graph is never going to cross the X-axis. And the whole point of this line thing is to be able to say, okay, this is one intercept and this is the other intercept, and these intercepts actually mean something. So in order to get to the x-intercept, we have to like make an imaginary version of the rest of this graph, which gets you down to now seeing this x-axis. But because we're on this side, we're on the negative x-axis. So this point is actually going to be -1 over Km. So whereas the y-intercept is going to be +1 over the Vmax, it's going to be -1 over the Km. So now we've also got negative and a fraction. So let's break what that would mean up even further. So let's say we've got a Km1 equals 5. And then let's say we've got Km number 2 equals 10. Then we've got 1 over 5 equals 1 over Km. And then we've got 1 over 10 equals 1 over Km. But I need to get it to be this -1 over Km, which means I'm going to just have a negative sign. So -1 over Km equals -1 over 5. And then -1 over Km equals -1 over 10. -1/5 is smaller or more negative than -1 over 10. So -1 over 10 is bigger, more positive than -1 over 5. So in contrast to what's happening with the Vmax, if you've got the V increasing, that means the 1 over Vmax is going to be decreasing. Here, because of that whole negative thing, first, yes, because of the fraction, it is increasing, but then this negative situation would mean that if this is higher, this is also higher. This is lower, this is also lower. So if you increase the Km, you're going to see a decrease in -1 over Km. I'm sorry, if you increase the Km, you're going to see an increase in the -1 over Km. If you increase the Vmax, you're going to see a decrease in the 1 over Vmax. So the y-intercept being the 1 over the Vmax, the x-intercept being 1 over the Km, -1 over the Km. And so then you can also figure out that the slope is the Km over the Vmax. You want to actually do the mathiness of this. The equation in general would be change in y over change in x. So then we've got the change in y would be the 1 over the V0. And then the change in x would be the 1 over the substrate concentration. And so if we do all of the flipping of the fractions and things, the substrate concentration would come to the top and the V0 would come to the bottom. So then you would have the substrate concentration over the V0. And that is how you would figure out the slope of the LB plots. Thanks for watching this video.